Well, hello. I hope you're enjoying the webinar. My name is Melissa Lenczewski, and I am a professor at Northern Illinois University. I am today going to be talking to you about the fate and transport issues of microplastic in the subsurface. You've already heard a lot of discussion about types of microplastics and some of the issues. Well, one of the things that the objectives for me for this talk is to look at sources of microplastics in groundwater, and look at the properties of them that impact their transport. So how are they getting into our groundwater? And then I'm going to talk about a couple case studies that I'm working on how did the transport of microplastics actually occur. So microplastics in groundwater. Well, one of the things that we've really come across recently is when we're thinking about microplastics in groundwater is the sampling equipment that we're using. A lot of it is made out of plastics. The PVC from the pipes that were, right here, this is PVC pipes that from wells, and these are our sampling. Here's some balers. And so just even us sampling might be introducing microplastics or might be confusing with it. But when we also look at microplastics in the environment, there's a lot of different sources of it where it can transport through soils and sediments and get into our groundwater resources. So when we look at microplastics, we look at them and we say, hey, look, there is a lot of dynamic sources that come from it. You'll hear other people talk about this too, is, urbanization, aquifer management recharge, the surface water, groundwater interactions fields, getting into our groundwaters and then ending up in our resources. At the bottom of all my slides are resources if you'd like to read the papers that are associated with each of the slides that I'm showing you. There has been groundwater research been done before. So yeah, there's been some studies that look at groundwater. This is just a picture showing the different locations that have done research projects, from the US and Canada around. They looked at different bore wells, karst systems, land conservation, and so it's becoming more and more obvious that when we thought about groundwater being protected because it was being filtered through the soil, we're starting to realize more and more that maybe these microplastics can actually get into water, into groundwater. So there have been studies that have been done. I'm just going to highlight a few of them for you today. There's one from Australia where they looked at microplastics in an agricultural area, so coming in from that source of pollution. And they found that the average concentration was 38 microplastic particles per liter, so in 1 liter of water or a quart of water. And the average size was about 89 microns, so very, very small. Bacteria is about 1 micron, and so, small sizes. Most of them were polyethylene and PVC, were the most commonly detected. Another project was done in India. This one, they linked together some of the hydrogeochemical processes, like they actually tested pH and conductivity of the water to see if there was a correlation. If we're looking, if it's easy for you to maybe measure conductivity, could you figure out also the microplastics, or is there some link? So there was a project they did inside of India where they sampled a whole bunch of wells in there, and they found no significant correlation between what we would say as water quality parameters and the quantity of microplastics. So they were finding them. Another paper was done in China, and this one they found a high abundance of microplastics detected in groundwater, but these were associated with anthropogenic activities, human activities. And in this case, a lot of it was landfills. Those are large, big things of plastic. And so when we're close to them, we actually do see that microplastics can get in there. They were finding different types of plastics that were most commonly found in there. Their sizes were less than 100 micron, and 4 of the sites out of the 8 accounted for most of it. And so they could link it to these different types of activities that are in there. Well, great. We know that they're there. They can get into our groundwater. Wonderful. But what impacts that transport? How do they migrate into there? Well, a couple different papers have looked at this issue. in there. So one of them was ionic strength and aging. So microplastics migrate due to being small sizes because there are, particles. So what they do is they move in the interstitial space between the grains. So you can kind of see that here, the microplastics moving between the grains. Also, the most things in nature, depending on the pH, there's a whole, we can go into a lot of it, but we're not going to get into it today. Negative charges. And so they were repelling each other because of negative and negative charges. And so they would repel, and so they would migrate. They looked at aging microplastics, so how old, like they've been sitting in the environment, being baked by the sun and everything. Well, what they found is that what it did was it put more charges on the outside of the particle and allowed for it to increase its mobility, how much it moved inside of there. And so when we look at aging, and then the other part of this was ionic strength. So ionic strength is like, do you have sodium chloride water versus calcium carbonate? You got limestone in your area. You got a lot of humic acids or organic, the soils. Like I'm in Illinois, the soils are black because there's so much organic. Oh, it's great soils, great soil. But so can these increase it? And what they found was that as they were adding more of these cations, so the calcium and sodium and the acids, that helped to retain them. So this is telling us that we really need to understand the system, the chemistry, and the age of the plastics. In other studies, they also looked at sand columns. So this is another thing I'm going to be talking more about. So, it's, do you want us to inject microplastics into your aquifer? Probably not. So what we do is we set up these column experiments. We take in my case, I used I went to the local hardware store. If you're from the Midwest, Menards. And we filled it with sand, and then we pump microplastics through so we can see the effects of this. So this is what they did here is they did sand columns. So they put sand into a piece of metal and then pumped water through. And they looked at 10 to 20 micron size particles of microplastics. So really, again, small particle sizes. And they were looking at flow rate. So as they're changing the flow rates that are in there, they could get, different, they were looking at that issue. They found that the larger the diameter, so the bigger the particle, less mobility, great. Filtration theory, the particles can't move through there. And they also found out that they increased this water salinity, decreased the output by 50%. Again, that ionic strength issue that's in there. And then the aging issue. So we're seeing that flow rate, the material that's in there, salinity, affect all the transport of these microplastics in the environment. Well, what I wanted to do today was highlight some research projects we're doing in Northern Illinois University. So we're looking at the types and shapes of microplastics on transport and column experiments. So again, these pieces of metal, from the hardware store. And then we investigated change in permeability. So one of the big issues that could be a problem with microplastics is what happens if they clog all of our aquifers and make it harder for us to pump the water out. So our research was with my graduate students. So, if you're in academia, all the research is done by the graduate students. They're the ones who sit there and do all the work. We just supervise. But our research objectives were to investigate how microplastics, so we looked at different types. We looked at polyethylene, that's your plastic water bottle. I should have one here. Don't. Polypropylene, polyamine, and polyester move. So did the types of microplastics affect it? Again, piece of metal. I'll show you some pictures. And then we investigated how microplastics shape. So one of the things that when I talked about those previous experiments, they really weren't focusing on the shape of the plastic. And you've heard from previous talks that these microplastics are coming in different shapes and sizes and all that kind of stuff. So we wanted to focus on the fragments. I'll show you pictures versus fibers, like thin fibers versus spheres of them. So little chunks of them, long stringy things and round things. Does that impact it? We looked at aging, we looked at the conductivity in there. And then if we mix plastics together, which is what we would find in nature, does that impact it? So, does one type of plastic stop another one or help it? So that's what we wanted to look at. And then we wanted to do this hydraulic conductivity testing to see, do they clog? And the concentrations we tested, would that clog the pores in there? So what we did was we did a column experiment. And so this is what the column, like I said, just went to the hardware store and then filled it up with play sand and got some gravel for the top and stuff like that. We pumped water in through the bottom to the top, and this is an issue that I'll come with later on into there. But we pump it in, and then we're using as much metal as we can and glass to sample with. We're pumping different types of microspheres in, different size ranges and densities. So this is one of the things when we're pumping from the bottom to the top. This pushes all the air out, and then since our polymers, some of them are less dense than water, they'll have a tendency to float up versus the heavier than water ones will stay at the bottom. So we need to work on that. So that's one of the issues that we're looking at. And then we put in around 77,000 microplastic particles per liter or per quart, if you want to think of it that way. And then we mixed and we put in 33,000. So if you remember some of those previous studies that I talked about, they didn't look at anything this high. So we were putting a lot of microplastics into these experiments, into there. Then what we did was we mixed in salt into there. So we put in a conservative site tracer so that we could see how fast the water was moving. We put them in there, and this is what it looked like in the laboratory. We color coded all the things, and so this is just my lab. We looked at fibers versus fragments. So this is what this looks like. So these are the fibers in there. So this is polyadenine fibers, polyethylene chunks. You can kind of see the chunks of it in there. And then what way we look at this in our studies was we did what's called breakthrough curves. What's a breakthrough curve? What we have here is along the x-axis, we have time. So this is when we injected the plastics is at 0. And then after 2,000 minutes, that's the end of our experiment. So we did this for 2,000 minutes. Along this axis here, we looked at the concentration of particles per liter. So this gives us our concentration of particles. And along this axis over here, this is our sodium chloride tracer. So this is our salt, because salt just moves right with water. So we use it as what's called a conservative tracer, because what it does is it moves along with the water particles. So if something is retarded or retained by the water, we call this retardation, then it is greater than 1. So 1 means it moves just with the water flow. It's just moving straight with that water, going through the column. If the number is bigger than 1, it means that it's being held in. So we refer to this as retardation. So we did 3 runs with the different particles, and then we calculated retardation rates, the capital R, and we looked at them for the different types of microplastics on their own. So this line that you see on each one of these represents like when that peak concentration came through. If you think of a normal distribution, this is the peak concentration versus, and then we compare that to the sodium chloride, our conservative tracer. What we found is that all microplastics are retarded into the environment. They get stuck in there, and there's really not much variation between them. So what we're seeing is that no matter, in this particular part of the experiment, no matter what we ran, we saw on average between 1.58 to the most retarded into there were these top ones, which were the ones that had the less density inside of there. But we all saw that they were retarded compared to a salt tracer. So we know that they're getting retained into there and that they come out later on. But so they're all being retarded in the system. Then we did an experiment where, again, here's my lab and here's all the different color-coded plastics. What we looked at this time was we put the plastics in and we used what's called a permeameter. This right here will measure what the hydraulic conductivity is, or how easy it is for water to flow through the system. And so we looked at hydraulic conductivity measurements before and after plastics were put in to see if that impacted. Well, again, same type of research project where we put microplastics in. We had what we called low concentration versus high concentration. Our low concentration is what we did in the previous experiment. And then this one, we were trying a much higher concentration because we wanted to see if that really clogged the pores, if we could get that to happen. Then when we did the experiments, sorry, I keep moving around the screen, but it keeps you awake. So there you go. What we did was we looked at the microplastics into there, the low versus high concentration, and then we had a blank because we wanted to make sure that we weren't finding any, like, how was this compared to if we didn't put any microplastics into the system. And so when we did that, we looked at the low. So in this one, these different colors along on the bottom here refer to the different colors of the column. So these three on the left are the low, the yellow, black, and white are the high. So this is the high concentration. This is the low concentration of microplastics. And then we looked at the different types of microplastics. So we did everything in triplicate to see if, want to make sure. And then this is the polyethylene spheres, the fragments, and then polystyrene fibers, and we looked at all the different ones, and then we compared it to our blank, which was our did not have any plastics into it. And so what we see is that here is the average change in the uncertainty. So we had very small, when we look at these numbers, this is the change in permeability. When we look at permeability, these are within log rate. This is a -7 log. And the variation is so small before and after that we really didn't see a change. That there wasn't statistical when we did this analysis. We couldn't find a difference between the high and the low in there compared to the thing. And so what we think is that absorption or straining really wasn't impacting it. That we did not see them clogging it by straining or absorption in these really high concentrations in there. So in summary, let's see where I can put me down in this corner here. In summary, the controlled column studies aided the controlled studies aid in understanding the fate and transport. We're still trying to understand all the results that we got and the next steps that we can do. And this is the first steps in examining possible consequences of these things. Microplastics were delayed compared to the conservative tracer, so that was that retardation that was in. Microfibers were retained the most, while spheres, so the little round ones, moved fastest, and fibers were retained the most. We think that they couldn't swish through there. They kind of got stuck around things. And then there was no change in permeability occurred under the conditions in which we tested. Again, maybe we weren't having the right concentration, or there wasn't the right conditions inside of our system to see the permeability changes in the aquifer. So we need to test different systems. So again, research projects. So we've always got work to do in there. And then I just would like to end with some of my thoughts on microplastic research projects for students in here. My thoughts are for the microplastic research, especially with fate and transport. So what impacts it in there? Microplastics are everywhere. So part of the problem is just trying to figure out how to do some of these projects. We need to understand the fate and transport. There has been what's called colloid theory. So colloid theory and colloid transport has been done before, looking at like bacteria sizes and viruses transmitting through that. But generally microplastics are larger and more ubiquitous than these. So can we, well, okay, well, that's fine, whatever. What we're trying to do is look at these transports inside of there. And so can we take some of the theory that's already been done and apply it to this new microplastics? it's really tough to do these projects. I'm telling you right now, just to be able to get the plastic into the system. As you can see here, this is a pressure transducer, and we had tried to do some field work on this, and they just stuck to everything. You can see them in the glass bottles in here and stuff like that. And then trying to figure out, how do I not have a system with plastic? I mean, the clothes I'm wearing right now got plastic into it. I mean, it's everywhere. So it's really hard to do controlled experiments. We need to be doing field blanks, equipment blanks. All of those things really need to get, because how do we separate what is being transported versus just what comes from our equipment, our clothing, our everything. So it's really hard. Microplastics stick to everything. They like to stick. They also float. So part of the other issue we had with some of these experiments was that they would float to the top, and then we try to mix the solutions and they wouldn't mix. And so they're really hard to get into there, so they float. So we need standard methods and reporting and blanks, and I think you'll hear about that, and hearing about that with the presentations here, really that we need to be standardizing some of these things. How do we report it? Is particles per liter the right way? Or should we be looking at grams? Making sure that we're doing all the correct blanks and blank processes. And so that's why we were trying to do column experiments, because we could control for some of these processes that are in there. And then column studies are just one type of project, but there's a lot of other research that needs to be done to fundamentally understand how microplastic transport. And you'll hear more about those in the next presentation. And with that, I just want to say thank you. If you'd like to get a hold of me, I'm doing research around the world right now, and so different places use different ways to contact people. So I gave you all of them here. Email is always like a good one. If you use WhatsApp, Line, Telegram, I'm on Facebook, I'm on Twitter, you name it. So if you have any questions about this, I can either answer them later, or probably better to send me a message, and then I can really get in depth into your question that's there. Or if you want to have a conversation about it, love that. So with that, thank you very much and have a great day.